Well, this graph is generating a bunch of rectangles under your curve called Riemann sums. And these Riemann sums can get thinner and thinner and thinner until their thinness reaches near 0. So the thickness of these rectangles reach so close to 0 that they give you an actual exact area under the curve, which is what we'll be talking about in the video today. So now that you guys have gotten past the animations, you're going to get into the more fun stuff. The numbers, the math. Isn't that more fun, right? I'm winking right now if you can't see my face, which you can't because I don't have a face cam. But what we have here is a limit. So this limit has n approach infinity. And we have the integral form here. We have the integral with the bounds b and a. And b and a, let's say we use the example function x squared. B would be the upper bound, 3, and a would be the lower bound, 1. So if I just draw this out, we write 3 and 1. And remember, these are just example numbers in this case. So we have the limit as n approaches infinity, and we have the n at the top of summation. Therefore, I approaches infinity as well, per the summation math. I guess if you don't understand what summations do, then I highly suggest you review on that, because if you're taking calculus 2, this will kill you. But what we have here is a function, and we have inputs into the function. This input is not important right now, but essentially what we have is f times delta x. And delta x in this case, as you can tell for the animation, delta x is the width of the rectangles. And as delta x gets thinner and thinner and thinner, the rectangles get thinner as well. And since those rectangles get thinner, or the subintervals, if you learn about Riemann sums, since the subintervals get thinner, then you get a better and better approximation. But what better approximation can you get than to infinity, if you have an infinite amount of rectangles? Well, if n approaches infinity, delta x is the subinterval width. And you can calculate the subinterval width by subtracting the upper bound from the lower bound. Subtract the lower bound from the upper bound. I think I said that wrong there. But when you subtract the lower bound a from the upper bound b and divide it by the amount of subintervals you want, n, you get the width of delta x, or the width of your rectangles. Well, if n is approaching infinity, and n is approaching infinity here, then delta x is approaching 0. That's basically what this is saying. And since delta x is approaching 0, we have super thin rectangles like this. They're essentially just straight lines. And what we have, again, in this sum is your function value. And this function value represents the height of the rectangles, and delta x represents the width. Well, if we have height times width here, we get the area that the rectangles take up. So if we multiply your function value, or your y value, height, by delta x, we get the area of the rectangles. And if we add those areas all together, we should get the exact area under the curve. And now, the thing about this is, the reason why this sum approaches infinity is because, due to the fact that these rectangles are infinitely thin, we have to have an infinite amount of rectangles in order, or lines, essentially. We have an infinite amount of lines in order to fill up a two-dimensional space. Well, now that I talked about this entire thing, we need to talk about the inputs. Well, the input is a, and we have an I in here. Basically, what this I is doing, so let's take everything out. Basically, what this I is doing is multiplying into b minus a over n. Right? And b minus a would be your length of your interval that you're trying to calculate the integral of. So it's the length of the interval. 3 minus 1 is 2, so the length of this entire thing is 2. So we get a 2 up here in our example problem. So you get a 2i times n. And what a does is start your x value, or your input, at the beginning bound, at the lower bound. So it starts out off at 1. So let's circle this. I think, does that go off the screen? A is here. And when you add all the widths of the rectangles one by one, like like delta x. So I times delta x. So when you add I, so I starts off at 1, and delta x is some very, very small number that's very close to 0. So when you multiply 1 by a number that's close to 0 and you add it onto a, you get the first line. And when you add the second number, per the summation formula, when you add the second number, so when I is now 2, you get the second line, right? So you get the x value at the second line. A is the starting x value. I multiplied by the width of the subinterval gives you each next line. So if I were to set up this equation, this limit, with terms to, wait, what am I saying? Well, related to x squared, so we're going to actually use our example, our summation limit would look like this. So I starts off at 1. This is n. And we have some function with a 1 plus I times delta x. And delta x is b minus a, which is 2 over n. So we get 2 over n here. And what we should actually get is 2i over n if we multiply the I into the fraction. And we multiply this by delta x, which is just 2 over n. But remember, our function f is x squared. So we need to square this. Right? Since a plus I delta x is your is your input. There you go. Is your input to the function. We replace this guy 1 plus 2i over n with x, with the function x in x squared. Now, basically, if you just want to answer multiple choice questions, I'll just give you some tips. The first number here, if you see some plus number, 1 plus something, this is your lower bound. Okay, so this is your a value, your lower bound of your integral. And if you see 2 here, then just add 2 onto your lower bound to get your upper bound. So 1 plus 2 is equal to 3, and this is your upper bound. And you should see 2 of these 2's. You should see 2 of them, because that's just delta x just appears twice inside of your limit function sum definition. And basically, in a multiple choice test, they're probably gonna ask you something like, what are the bounds of this integral? They're gonna give you some function. They're not gonna give you the function. They're just gonna write f of a plus I delta x times delta x, and you could just interpret the first number as a, which is the lower bound. Your second number, or the second integer you'll probably see inside your form, is 2 in this case. And we just add 2 onto 1. Now, if 1 doesn't appear, like for example, this is not, and nowhere, you can imply that it's a 0. Therefore, the lower bound is 0. So if you got something that looked like this, all right, let's write that better. If you got something that looked like this, where you just get 2i over n, and you don't get some whole number added onto it, like 1 plus, then you can pretty much safely assume that the lower bound of your integral is just 0. So 0. And if you want to find the upper bound, of course, you add the lower bound onto the number 2, or the number on top of the fractions that you see outside of here, and you get your upper bound. But I bet you guys, well, I hope after all this explanation you guys get it. This video took a very long time for me to think about how to teach it, because it's just so, summations are such a tricky topic, unless if you took like calculus 2 already. It's just something that a lot of people aren't familiar with up to the point of calculus 1. And I really hope that this video helped, because I had a lot of trouble learning about this when I was taking calculus 1 last year. But as always, if you have any questions, put it down in the comments section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.